Hi, folks. I'm Sean from CMCL. CMCL is the translator for this use case, and we have an industrial partner who is ArcelorMittal. So ArcelorMittal are a multinational steel manufacturing corporation. Now, while the process of taking a single piece of steel and rolling it into a beam has existed for well over a century and a half, the challenge of innovating on this and improving it is still very much a current one. Current challenges that face the industry include there are new mechanical properties that are required, new grades of steel, new cross-section, or shapes. There is pressure due to increased energy costs and material cost. So this is what made this use case really exciting as well. So the first step in the first translator step is to gain a good understanding of the business case. So quickly, what became clear that was really important in conversations with AM was that a well-controlled and optimized production process was critically important. And due to the scale, even a really small improvement could lead to huge changes when this is scaled up. As well as that, this will only become more important into the future due to tackle such problems, as I mentioned, as rising energy, materials costs, as well as CO2 tariff costs. There's a lot of investment made in testing and doing post-analysis. So digital tools that would assist in that would suggest different areas to investigate in actual experiments would greatly reduce the cost of these experiments. So the second step is to gain a good understanding of the industrial case. So you've seen this diagram or similar ones for the previous use cases. So we see here that we start off with molten steel, turns into a beam blank, then that is rolled through two rolling processes, the blooming and the tandem, and then this is quenched and cut into and sawed into daughter beams and beams that are used for testing. And we see there also all the processes acting on this beam. Now, at this point, it's really important to note that it is clear that there's a huge number of variables here, down to the temperature of any of the steel at any of these points, the temperature and of the water that's quenching it, the speed of the water, the time in any of these processes. There are a huge number of variables here. So as we've seen before, this is translated into an EMMO compliant ontology. We see up the top, we have the process conditions. So that's things like the rolling, which is split into two subclasses, which is the blooming rolling and the tandem rolling. And all of the processes we saw in the previous diagram. On the bottom there is another element of the T-box. So these are the stages of the beam at various stages. So what's in there is the concept of the molten steel and the daughter beam and its various stages there. And in the middle, we see instances of these, and this shows how this is all connected together, how the process conditions and the beam is all interrelated. So the challenge that we came up with was twofold. So we split it into two separate ideas. So there is the forward problem and the inverse problem. We sometimes confuse things by calling it the backwards case or backwards problem, but that's just nomenclature there. They're all the same thing. So the forward problem is to predict the final properties, mechanical properties of the steel beam due to the input properties that were used to create it. For instance, all those temperatures and times I was discussing before. So that would obviously be exceptionally useful. But I think what's more exciting is the inverse problem, where we set out a number of KPIs, a number of things we want to optimize on So some mechanical properties that we would consider desirable, and then find the optimal input properties that we can use to create those. So we wanted to use a data-driven model. So we needed to get a lot of data. First step was the collection of that raw data in the plant by an experienced AM R&D engineer who's worked on these kind of projects before. And then this was communicated to us as translators. We performed data cleaning, correlation analysis. We went into great depth on metadata analysis. This gave us a fuller picture of the industrial and business case. And this was all communicated back to the other partners in the consortium. Going into exactly how we addressed both problems, we see the forward problem here. So we used the data that I discussed previously to and fit a fast response surface to it. This using a HDMOR algorithm. This was then evaluated at various points, and this essentially gave the final mechanical properties. So this then addressed the forward problem. The backward problem is a tiny bit more involved. So we used that same model, and we performed multi-objective optimization on it. So we got a set of points that were in some way optimal in these multiple different KPIs that we had laid out. I should also mention at this point that I'm being somewhat evasive over some of the details regarding the exact KPIs and any results. That's due to some confidentiality concerns with the public workshop here. But anyway, this still gives a complete idea of the process we used. So just back to this, then we had this set of points that were in some way optimal. And then we used a multi-criteria decision-making algorithm to distinguish between these, to rank them and to find the best results. So do we care more about final mechanical property A or B? You could give all those weights and limits. So yeah, that was the backward problem. Then putting that all together and putting in one kind of complete picture here, we see, as I said, the data was used to create the model using a HDMOR algorithm. Then for the forward problem, a number of input conditions were specified, and the model was evaluated at those points, and the final mechanical properties were then evaluated. Then for the backward problem, certain parameters were chosen to be optimized on, and limits were placed on them, and then the model MU was performed on the model, then NCDM, then the optimized mechanical properties were found, but not only that, but the input properties that would make steel of that grade that is required. So onto model validation and communication, kind of, is this any good? So we use the very standard technique of dividing out our input data into a subset, and then the rest of the data was used through the process that I described there. And then this model was validated and compared to the randomly selected subset that we'd set aside before. This is then all, once we're confident with this, we communicated that back to the AM team. And the next step would be for them to actually perform these experiments, like make these steel beams that we recommend to use the forward problem. And that is something that we're really excited about. And the backward problem, especially, that would suggest new areas to explore in terms of their input space. So just looking then at the components that we used for an on-platform execution, the mods agent was used. So the model development suite is a piece of software developed by CMCL, and mods agent is just a REST API that for mods. So this is performing all of the model generation, the optimization, and all of these processes. Those involved in Open Model would also recognize this. We're also using these developments there. And in fact, due to the synergy between the architecture in both projects, we are developing different functionalities in each project, but making those functionalities and those features available to both, and we hope more projects going forward. So then what handled all the semantics, the marking up of the data semantically, and handling the submission of the jobs to the mods agent, returning the results, and so on. That was all done by the App4 interface, and this was enabled using Symfony CUDs, which I think was developed in another European project. So just a brief note on CUDs and Delight. You may have heard Delight discussed as well. And these are two interoperability frameworks that are in fact used in this application. I won't go into a huge amount of details in the interest of time in both of these, but one of the key pieces of innovation that will be really useful also going forward is the development in our understanding, and indeed the methods we use and the hard work from across the consortium to allow these two interoperability frameworks to actually interoperate with each other in a way. So then finally, how this all works together. We have the user interacting with the UI. They select the task, forward or backward problem. They select a set of data. This is all processed using the CUDs to Delight interface I was talking about before into a CUDs object. This is given to the App4 interface, which then communicates, as I said before, with the mods agent, and then all this data, the results, are sent back the way it came. So finally, what advantages were brought by OntoTrans? Well, one of the key ones, and one we're really excited about, is the complete ontological description, and the EMMO compliant description, in fact, of this process. So this enhances our understanding of the industrial case, as well as allows interoperability into the future. This will also allows users to explore the data themselves in a standardized way without necessarily prior knowledge of any modeling software or any modeling techniques. So we can give that power to decision makers. So also OntoTrans, as discussed throughout today, has access to post-processing tools and tools to analyze the data. That's really important for us. And something we're really, really excited about is, for instance, in the EMMO, it is not a description necessarily of our particular use case, but in fact a description of the plant on the ground. Like it doesn't describe precisely the forward and the backward problem, but it describes the reality of the situation. And therefore, this allows us to extend this into new areas. And the extensibility is, and how we can use this into the future is really exciting for us. So thank you.
Thank you, Sean.